Morning. It's the physics video lecture, Physics 105B video lecture 12. And what are we doing today? Small oscillations. We're going to wrap that up, and I want to maybe pose one more really interesting problem that we'll work on together a bit, and then we'll move on. But I think that'll take up most of this hour. So we're doing small oscillations. We have a formalism for it now. We've solved this amazing problem. Small oscillations. Many degrees of freedom. And I'll repeat what we had ended with, because we ended with the following expression. x1, x2, down to xn. So we have n degrees of freedom, and x of t, of course, is what we're looking for. And we were able to put it in this matrix form. So I'll go to the matrix form here. This is A11 out to A1n, AN1. And we have an n by n matrix, and these columns are the eigenvectors. So this, for example, is the eigenvector a sub 1. This is the eigenvector a sub n to the eigenvalue eigenvector problem. And then we would have here alpha 1, I better leave myself a little room, alpha 1 e to the I omega 1 t all the way down to alpha n e to the I omega n t. So there's our solution, the system of linear differential equations with constant coefficients. Has this very nice solution here. And we're just going to have to imagine the matrix multiplication here. Let's just look at x sub 1. x1 of t, a11 alpha 1 e to the I omega 1 t, all the way down to a1n alpha n e to the I omega n t. So x1 of t is a motion of the single at 1 degree of freedom, but it's very complicated because it's a combination of n different frequencies. We did it with 2 frequencies, and we were able to tease out some real order, and we'll talk a bit about why we were able to see the order in the thing, even though, this single thing just looked at on its own would be a very random, wiggly, oscillating thing. So it's a combination of all of these eigenfrequencies, and of course the real parts is all just sinusoidal. Now, here, I'll send this up to the big matrix. What we saw was that there were these things called normal modes. So we had normal modes, and those were the collective motions of the system that were associated with a single frequency. So in our 3 spring 2 mass system here, which I'll just, okay, that's a bad sketch. No point in such a bad sketch. Let's try again here. So we have these 2 masses connected by K prime, no friction, connected at the ends by the spring K. What were these normal modes? They were the motions against each other or moving together. So those were motions of the system, you could call them collective motions, but they were associated with a single frequency. And this setup up here can also be interpreted that way. So this is just for a reminder. If we have x equals matrix A times vector, I'll call it capital Q, right? Let that column vector be capital Q. You see, this can be seen as a coordinate transformation as well, because these were the original coordinates, and each of them is a new coordinate as well. Okay? Could be thought of as a new coordinate, right? This is, after all, a time dependence. Time dependent. So what we can do is isolate these by multiplying both sides by A inverse. So we have an inverse matrix times X would be equal to A inverse, no vector there, A inverse A times Q, which is to say this Q is this inverse matrix applied to the original coordinates. And each component of Q oscillates with its own frequency, but it's a major mix of all of these motions here. So a single frequency for each component of Q. And the ones we saw with our 2x2 system were, again, the ones against each other, the ones in phase. And what demonstrated that, or what gives us that, is these eigenvectors. Remember, we had 1, 1, and 1 minus 1, which describe these normal modes. Okay. So there's a lot more that can be said about normal modes, but at this point I want us to have seen it and understood it as a property of the eigenvectors, and the fact that, I'll put this in words, each component of Q has one frequency each component of X, has the full n frequencies. Only one frequency. Okay. So yeah, I just wanted to expand on that a bit. It's possible to rewrite the Lagrangian in terms of normal modes and normal coordinates and things like that. We're not going to do that. Just make sure you realize the role that the eigenvectors play here. Okay. So I should put some words there. The column vectors are the eigenvectors. The columns of the matrix are the eigenvectors. And good. Okay. So now I want to show this last system that we're going to discuss. It's a version of the one we've done. It's a little bit more interesting in terms of what we have to apply. So we're going to do a two-coupled pendulum system, except the coupling will not be a spring. So I'm going to call this homework. I'm going to work quite a bit of it with you guys. So homework, coupled pendulum. Here's what we have. Let's label this. We have the one pendulum, got a mass, a length. We've got the other one. I'll have them towards each other here. There's an angle phi sub 1. We've got an angle phi sub 2 up there. So how they're coupled is that they have some electromagnetic charge, some electric charge on them. So we don't just have M, we have Q, and we have Q. Okay, but we're going to keep the length the same, the mass is the same, that's a comma there. Okay. And the charge is the same. Well, the charges we have to Q1, Q2. Mass is the same, charge is different. Because we want the case that the pendulum, we want the case that the interaction would be attractive or repulsive. That's what we're looking for. So we need a separation here, and we want the small oscillations and the coupling. So coupled pendula, electric charge, electromagnetic. It's an interesting one. So we want to set up the Lagrangian and get the small oscillations. Okay, small oscillation frequency, just the way we did with the pendulum system. Right, we did this one. Your assignment is to show the pendulum system's equivalent. You'll also find that this one's equivalent, but it's going to be a little bit more work. Interesting problem. So here we go. The kinetic energy causes us no problem at all. So I actually will formulate find L small oscillations and the characteristic frequencies. Lagrangian small oscillations, Lagrangian characteristic frequencies. Okay. Kinetic energy, of course, is no problem. T is going to be 1/2 m L squared V1 dot squared plus 1/2 m L squared V2 dot squared. Okay. The potential energy is a little bit different though, because we have U is equal to mgy sub 1 plus mgy sub 2. Right, we'll turn those into angles. But we also need plus the electromagnetic potential, and I'm just going to say plus Q1, Q2, 4 pi epsilon naught R sub 1, 2, right? That would be the electrostatic potential between two charged spheres. And R1, 2 would be the separation distance center on center. So this thing here, turning this into an expression in terms of phi1 and phi2, and then expanding it to quadratic order is an interesting problem. So how much of this do I do? I'll just remind us that we can say minus mgl cos phi for the simple pendulum. And this would be cos phi sub 1. We'd have the same thing for this. When you expand this to second order, and generally, cosine of phi 1 minus phi squared over 2 plus, smaller terms. So that's when you expand the cosine. It's not going to give any trouble, and you can add and subtract constants as you need. But eventually, we're going to want that stereotypical potential energy. So this is going to cause no difficulty. This here we're going to work on a bit more as well. Okay, good. So I'll just write here the electrostatic potential. The electro So first thing we can do with this Q1, Q2, 4 pi epsilon naught, R12, we can just say it's alpha over R12. Alpha can be positive or negative. Yeah. We know that if we have unlike signs here, we have attraction. If we have like signs, we have repulsion. So note attraction / repulsion. Interesting subtleties, because the attraction and the refractive and repulsive case give slightly different expressions. Very interesting. Okay, so what else now? This R12 has a function of phi1 and phi2. So what we have to do is find R12 separation distance as a function of phi1 and phi2. And in the limit of small angles, it'll clean up quite a bit. If you're trying to do it right now with Pythagorean theorem and stuff, it would be a pretty hairy thing. But we find that, but of course it's in the denominator, and then we have to expand, okay? So those Kij, okay, before I go on, so we have this, find this. Here's a couple other notes. In terms of this, when we do our expansion, we're going to find a problem here. The equilibrium is not at phi1 and phi2 equals 0. Equilibrium for the total potential, right? Potential is not at phi1 equals 0, phi2 equals 0. Because there's that little bit of attraction or repulsion, they would either be kicked in a little bit or kicked out a little bit. And what we'll find is we wouldn't be able to do that algebra. The algebra that has to be done there is too difficult. So we want to use these values anyway. And that means we're just making controlled approximations. In other words, if the electromagnetic interaction is sufficiently weak compared to the weight there, then these angles will be small, and we can approximate our values in our expressions that we gain. We can approximate them with phi1 and phi2 equals 0. So I'm going to write here, that's comma, but use phi1 equals 0, phi2 equals 0 when evaluating expressions. Okay. And is that cheating? It's not cheating, because these things are controlled, and we can give we can gain expressions that tell us how many percent are our results off, how many percent error is involved. Because, if the mass, and there are relations between mass, so if the mass is sufficiently large compared to the charge, then these things will hang almost vertically, and that can be controlled. Some quantities will be much less than 1, and you'll know what's going on. Okay, so let's see. I'm going to continue working this a bit, because it's such a good problem. So now what would our potential energy look like? You are going to have minus mgl cos phi1 minus mgl cos phi2 plus alpha over r of phi1 and phi2. What we're looking for is this: du d phi1 equals 0, du d phi2 equals 0. This is your equilibrium. Okay. And I just discussed how you're not actually going to find it exactly at phi1, phi2 equals 0. You'll find it at something close to that. What we need for our problem, remember, we essentially already have the M matrix, right? The M matrix is just a diagonal matrix, no problem there. For these Kij's though, right? Kij, we need d squared u d phi I d phi j evaluated at equilibrium, even though it's not the true equilibrium, we'd still find a criterion for when we can do this. So we definitely need the expression for this. This is going to be the tricky one because you've got the thing in the denominator. These are trivial, phi squared over 2 expressions. This one here you have to do a little more work for. And remember, these are constants. I'm just bringing that up because sometimes students will put in a bunch of functions, but they've been evaluated at 0, 0, and they're just the constants. And I'll erase and just remind us what we're going to find. We're going to look for minus omega squared m plus k determinant equals 0. And we write it in words so that it's there. The determinant of this expression equals 0. That's going to give us omega 1 and omega 2. And we already know this M matrix is going to be ml squared 0, 0, ml squared. This K matrix, that's the big question mark. Of course, in the limit, as the electrostatic interaction goes to 0, it'll decouple completely, right? You'll lose, you'll just end up with 2 simple pendula. So these 4 objects, we have to get the second derivatives of this thing right here. I'll even give a hint here. So I'll give a hint. I'll tell you anything. This alpha over R is going to look like this. The separation distance, we need this thing right here. Right. For small oscillations, you really can just deal with the horizontal aspect, just like I said for the connection with the springs. So you're looking at something like the separation distance, magnitude of, it's just L phi, it's D minus L phi1 minus phi2. This is what your complicated expression would simplify to as the angles get small. D minus L phi1 minus phi2. Yeah, I think that's, because it's a difference, and we're already subtracting D minus L phi1 right here, so I think that's the expression there. And it's absolute values, but if you construct it right, you ditch the absolute value. Okay, so that's easier to work with. Let's put a box around here. And it's 1 over this, so remember you're expanding this thing to second order, so you're going to have your phi1s and phi2s up in the numerator. So, yeah, I think that's the last thing I'll write down. Just as a reminder, you're ending up with, when all is said and done, U is equal to 1/2 something V1 squared, V1, V2. So these mystery quantities in the parentheses there. V2, V1. This is what happens after your Taylor expansion. V2 squared. That's what you're trying to get. And of course, this is what you populate this matrix with. Okay. Such an interesting problem here. Because it's interesting because it involves a lot of judgment to make it all work. Nothing is exact, and yet, we're doing physics. We want to make sure we understand everything. But you can even see, the criterion that we're looking for, or part of the criterion, is that L phi is much less than D. L times phi is much less than D. Because then you're changing this thing very little, and when you set those equal to 0, you just end up with D down there, and in your derivatives. So that's part of your criterion. And the second part of the criterion is to relate that to, M, G, L, and alpha. So this is one relation. You'll get another relation between these things where something's also much less than 1. Okay, I'm going to leave it right there, and you guys give it a try. If you have questions, let me know in the email, but you should systematically be able to make your way through here. And this is one I may just do on the board later on anyway. It's an interesting problem. Okay, so now we're going to segue into a new field of physics, one way or the other. This was our big application of Lagrangian mechanics. So I want to do one more application here before we leave the topic of small oscillations. Maybe I'll put as one more homework problem. We'll do the application first. What we're going to do now is, instead of 2 masses and 3 springs, we're going to have n masses and n plus 1 springs. Okay. N masses, n plus 1 springs. And so our system will have a whole lot of identical masses, m, of course no friction, m, and the same springs all the way down to the end here. K, and so forth. So actually I do have to draw a couple more, and then all the way up to here. So we want to find a Lagrangian for this system here, n springs. So what we have to do is call this, say, the jth spring, j plus 1, j minus 1. And for the kinetic energy, T is just 1/2 sum over m xj dot squared, j equals 1 to n. So there's our kinetic energy. What about our potential energy? Now the thing with the potential energy, if this chain is long enough, you know, there's going to be a difference at the two endpoints, but otherwise we're just going to have generic difference terms the way we had in our other system. So we could have 1/2 k x j plus 1 minus xj squared, and ignore the n terms. We'll just say we had j equals 1 to n, one to n minus 1, and then we could even take the n terms as well. Then we'd have 1/2 k x1 dot dot x1 squared plus 1/2 k xn squared. Okay. Because so there, we actually have it completely. Identical masses, big chain of them, identical spring constants. So we actually have our Lagrangian here already. So L equals T minus U. Those are independent coordinates. Point is, though, when we go for the Euler-Lagrange equation, we won't have to worry about the endpoints as well. So now we have to do next Euler-Lagrange equations for this thing. N mass is n plus 1 springs. X-axis, I'm just going to write one-dimensional. So what are the Euler-Lagrange equations for this thing? So since our index is j in each of these cases, we have d dt dl, choose another index, xk dot minus dl dxk is equal to 0. And there's a whole bunch of those. And like I said, the end ones we're not concerned with. We're really just concerned with what's going on in the middle. And let's go ahead and look at this. So dl dxk dot, this one's easy. We just go out here to the kth index and we end up with, we can even take the time derivative already. That's going to be m xk dot, and then the time derivative second one. This one's going to be a little more tricky. L dxk, or minus dl dxk, because what we're going to find here, when j is equal to k, we have k xk plus 1 minus xk. But we're going to get a second term here as well, because we have the xk plus 1 minus xk, and then we have the, oh, and by the way, this one here is an inner derivative, since that was our derivative, so one gets a minus 1. But then we also had another term here. I should actually write that out first. I'll do that in red. So what we're looking to deal with is 1/2 k xj plus 1, but 1/2. That's what we're feeling. We have two of these. 1/2 k xk plus 1 minus xk. We also have the 1/2 K xk minus xk minus 1. Right, so the xkth index shows up twice here. Here it shows up, and we got this and took the derivative. And on this one here, it shows up here. So then we have plus k xk minus xk minus 1. We've chosen different subscripts, a lot of k's in there. But that's our equation. And we have coupled equations. Minus is plus, so we actually have two of these x of k's, and then we have an x of k plus 1 and x of k minus 1. So let's go ahead and write this out. So let's write out the Euler-Lagrange equations. We have m x k second derivative. Maybe I should switch letters to I. Equals, and then what we have over there on the right side. I didn't have to write that. So what do we get here? We get equals okay, I'm going to leave it right here because what we're going to do next is not an exponential ansatz for this, although that's possible. We're going to reformulate this into a partial differential equation. So I'm going to write here next, convert to a PDE. Good, we'll pick that up next time. I did want to add another homework problem to this mix-up here before we leave this. So we know that these n particle systems, any time it's greater than 2, it's going to be a difficulty in terms of determinants and stuff. But some systems can be done, and it turns out that the system with 3 masses and 4 equivalent equal springs can be done. So I'm going to assign this one and say a couple words about it before we do that. So we have K, M, K, M, K, M, K, K. So 3 masses, 4 springs. x direction. And it turns out that, so let's just write find L small oscillations, and then frequencies. Frequencies of oscillation. Okay. So that's a homework problem. Now let me just lead us through a little bit of the discussion. First of all, we have 3 degrees of freedom. It could be bad. Okay. Determinants, not so nice, right? Third order polynomials, also not so nice. But this one, turns out one can do it. I want to draw your attention to the physics here because we can guess one of the solutions at least. Okay, we can guess one of the solutions, namely one of the eigenmodes. I'm going to say is going to have to be, you'll discover it, would be if this mass were at rest and these two were oscillating in out of phase, okay? Because then it would be 1 mass, 2 springs K. So one of the solutions, one of the frequencies on physical grounds must be omega equals root 2k over m. So if you were faced with a difficult mathematical problem, your physical insight would tell you, well, that's one of the roots, and that would be enough to get you the other two, because you turn a cubic into a quadratic equation. It turns out that this is going to factor out in such a way that you don't fundamentally need that physical intuition, but it's good to be aware of, because that's that's an extra trick, so to speak, that allows you to get through more difficult math. You can bring in physical arguments. So once again, if the middle mass is nailed down, so to speak, these two are just going to, and these two are oscillating symmetrically, then each one of their frequencies is going to be 2k over m, and so that will be root 2k over m. That'll be one of your solutions to this problem here. Other than that, it shouldn't be that difficult. You'll remember that there's energy stored in the ends, and then the energy stored in the middle springs is due to the x1, x2, x3 is due to the differences. So you just look at the way we did 2 masses, 3 springs, and extend it, and carefully write everything down. You'll get frequencies here, one of which will be like this. Okay, good. Let's call it a day. We're going to come back to this problem, and I have one more theoretical discussion about this whole business, and then we'll be ready to move on. Okay, see you guys next time.